Great. This is the lecture 4.2 on coordinated representation. The goal today, we'll do a quick recap about multimodal joint representation, what we discussed on Tuesday, and then start discussing coordinated representation. And to study one, or in fact, quite a few of these, I like to do a mini tutorial reminder on multivariate statistical analysis, including multivariate and covariance. And then that will allow us to study one very popular approach, which is the canonical correlation analysis as an extension to the simple just correlation analysis, and also some of the future extension that came after that, including deep CCA and deep CCA autoencoder. I will also look at multiview clustering. It's a very interesting aspect of almost of an unsupervised approach on how do you analyze multimodal or multiview data. And then look at an interesting paper that is also one of the reading assignment. I will just give a high level intuition about this paper. So it brings some interesting aspect. Within the spectrum of multimodal coordinated representation, CCA may be a little bit closer to joint representation. Autoencoder is a little bit closer to the unconnected, completely unconnected views. Quick recap. We looked at quite a few last week, on Tuesday. We discussed the generative models. Generative models are interesting because they allow you, if learn and train within the details on how to do training, which we'll discuss more in about 3 or 4 weeks. But if you can train a generative model, the interesting aspect is that you can almost translate in any direction. So you can generate from image, generate images conditioned on the text, or on the opposite, you can generate text condition on the image, because the advantage is that because we model the full joint distribution between X and Y, that allows us to do a lot of these interesting conditional probability or translation tasks. We can use these representations that we learn either through generative models like Bozeman machine, or some other ones which we'll discuss, other unsupervised approaches. And then once you have these, then what's interesting is that you can later on just learn maybe 1 or 2 layers on top of it to do another task, like a supervised learning task. In this case of the paper was looking at image retrieval from that. We look at another way to train these joint representations in an unsupervised way, one of them being stack autoencoder. And if you remember, you can learn end-to-end. In this case, the loss function is a 2-part loss function. One is how well you generate text, how well you generate images. You can train it with both image and input as image and text as input, or you could decide to train it just with the image as input, but still have your loss as text and image. I think that was one of the questions at the end. There's also the idea of learning these intermediate representation with the feed-forward neural network, where you are doing a translation task. So here you're not looking at training or learning the joint, but more the conditional probability. And so you're using, in this case, like the image and encode the image to be able to generate the text. That's for, like, example here is image captioning. And so at this point, then the middle representation is expected to be an intermediate representation between text and image. In practice, often this one may be closer to the text, closer to the image. There's nothing that enforces it to be really a joint representation. But it is definitely somewhere in between image and text. So, and then we discussed the fact that some of these representations don't explicitly model like all of the different ways you can interact. And so we look at bilinear models. One example of that was the tensor fusion network, which allowed us to do both unimodal and bimodal. And although it increases kind of the number of parameters, like it allows us that each of these are a little bit more representative. So it may end up being easier for the later stages of the network to find out which either unimodal or bimodal features are the most useful for the task. So and that's also aligned with some architectures where sometimes the input even in the multi-layer perceptron, sometimes people will extend the number of neurons before finally summarizing. That's maybe a little bit the same intuition you should have here. But how can we learn even better representation? I think better is probably debatable, but at least different type of representation. Coordinated is this other type, and if you remember coordinated, the idea is that not only instead of finding only one joint representation, then maybe you learn one representation for each modality and you find a way to coordinate it. We talk about ways to coordinate it very strongly at the end of the meeting on Tuesday, where you ask them to be the same almost, with cosine distance being your loss function. And this is, although it's sometimes called unsupervised learning, the unsupervised learning is a little bit misleading because it still needs some supervision, and this time it's the pair. The pairing between image and text is still needed to be able to learn these two separate representation. I call them separate, but because depending on which similarity metric you use, if it's a very strong like cosine distance, these will almost be equivalent. So, and we showed example, and that's the same example that we showed at the beginning, and now we can probably understand it much better what is happening, because really what it was is that you had pair data of image and text, and for each you have an image and a description of a text. And so from the image you may get a CNN that encodes it up to maybe, in fact the input may be just the CNN features, and the input here could be just the word-to-vec average over the whole sentence. And then the goal is to learn from these, learn new representations in such a way that they're as close as possible, their angles as close as possible. And when you do these, that was the beauty of this 2014 paper, where they were able to train on the pair data, and then at test time, go ahead and take an image and push it forward, like in the feed forward, push it forward, push it, this image forward there, get their representation, take the word blue, take its representation, take the word red, take its representation, and then do some arithmetic. And then you can sample from there the kind of images that are the closest. So now you can understand better that Vizim paper, this visual semantic embedding paper, and you could do it on the day and night. Now, these will not work perfectly, and that's one of the issue of this. They need to, although they are trained to be close to each other, they will not work for every possible word. This you cannot just do minus day plus color. So then suddenly you will become in a space that is no more the same region. So this arithmetic is not perfect, but it's nice to see some of this working. When you train these, you can also train them, and I think one of them is even a paper, either an optional paper or reading assignment, is the idea of also keeping ordering when you learn those structures. So you have those two embeddings, and then you say, I want them to be coordinated somehow, and maybe you say, hey, every caption, like I want them to have cosine similarity between image and captions. That's the way we just described. Or you could just say orderer embedding. So this case is that it's more of a structured way to putting that coordination. You may want, in fact, that if it is the same entity at a very high level, that these two are about persons, then yes, they are close to each other. Maybe the caption talk about I don't know, a farmer, and the image is a skier. So the farmer and the skier, they're in a sense they're not exactly the same, but at a very high level, they're both people. And so the entity, the idea here is that these should still be related, these two examples, but maybe not as closely as if there was talking about a skier and language and also seeing a skier. And so that's a little bit the intuition with this kind of more structured approach into this. And another way of doing it is to say, I have these texts and these images, and the way I will connect them together is through some kind of coding mechanism, like a hashing table. That will also allow me to be both efficient and also enforce some of the similarity. It will also bring a binarized version of that similarity I will force between that. So these are other examples. I want to also discuss about CCA and some of the others, but for that, I need to introduce or remind you about some of the things I'm sure you learn in undergrads, but I want to just be sure we're all on the same page. And it's about multivariate statistical analysis as a building tool for these coordinated representation. So multivariate statistical analysis, sorry, statistical approaches to understand the relationship in high dimensional data. Multivariate is, you can see it as multiple variables or multiple dimensions in your data. Example, a very popular, there's the ANOVA, and then there's the multivariate version of ANOVA, the MANOVA. PCA and factor analysis are other approaches under the umbrella of multivariate. And then LDA, a linear discriminant analysis, I will not discuss as much with Aldo, but it's a good reminder if you could look at it also, and we'll discuss CCA in a second. But the core of this are random variables. Random variables, a variable whose possible values are numerical outcomes of a random phenomena. And as you probably remember from previous courses on this topic, there's two types of random variable: discrete random variable. In this case, the values that this random variable can take are discrete, so 0, 1, 2, 3, 4, or they could even be colors or age or other type of, so it could be attribute or numerical. Continuous will be when it's an infinite number of value, continuous value. So examples, someone's age, someone's height, someone's weight. Age could be represented as a continuous, but age is sort of often represented as a discrete variable. Height could also be continuous, but often is like, oh, I'm 5 feet 11 or something, and the weight similarly would discretize a lot of these. But the interesting thing is also which one are correlated with each other. Age may be correlated, at least at the beginning, age with height and weight. Height and weight by themselves could also be correlated. So correlation is a very interesting aspect when we look at random variable. So given two random variable, I want to define a few terms. Expected value, that's something you will hear quite often, and I want to be sure that you have a mental image of it. It's the probably weighted average of the values. So if it's a discrete space, so I have all my possible values, and here it's for the discrete case here, but for all my possible values, and it's multiplied, I have a discrete number of these values, and it's multiplied by how the probability of that value itself of happening. In many cases, that probably may be just equal for everybody. So in that case, what is it equal to? Then it's just, if it's the same for all observation, then this is exactly the same as just an arithmetic mean. So the expected value could be seen as the mean in many cases, but if some samples or some values are more likely than others, then this will allow us to take this into consideration. So variance comes as the next version after that measure the spread of my observation. So it is the expected value of your data minus the mean and squared. And so that's the variance of your data. Variance is equal to the square of the standard deviation. That's another way to see it. Variance is going to be important when we also start looking at covariance and also at correlation. A lot of time, if your data is already normalized, or if you already remove the mean, then your variance is just almost a multiplication of your data if the data is already centered in this case. The covariance is where things start being interesting because you measure how two random variables change together. And that's interesting. So you have one random variable, you have another one, and then you're trying to see how are these two run, like how these two changing together. Here at this point, all of this is for univariate, like I'm not yet doing the multivariate. But in a second we'll show that. But if it's only X is one dimensional and Y is one dimensional, and you remove the mean, so you remove the mean from both of them, and then your question is like, hey, how is the if my X is suddenly increasing, how is my Y changing? And if my Y is changing, how is the X changing? So that's the and that's if it is already normalized data, then it's only the multiplication of the two. So the multiplication will become important because multiplication, the correlation, is just a normalized version of the covariance. The correlation, which measure the extent to which two variables have a linear relationship with each other, really what they're doing is just a normalized version. It's looking at the covariance, it's like how much they change together, but you just normalize it on like how much X changed by itself and how much Y changes by itself. By normalizing it, what's the nice thing is the correlation will be between 1 and -1. So you get a nice, because you normalize it correct nicely. So let's do a little test of these. If X is the horizontal axis and Y is the vertical axis, and I show you a plot like this one, will you say X and Y are both, and each dot there is one of my sample. So these are scattered graph, that's one way to call them, and these are each of my plot. And while if I have something like this, will you say they're correlated? And so in this case, it's very strongly correlated. Every time there's, in fact, it's, you could say positively correlated. So every time there's an increase in X, there's also an increase in Y. And as you get here, they're very scattered all around. And so at that point, you lose and don't have a strong correlation. So this was a bit easier. Now this one. So this one we knew is positive correlated. Yeah, are these also correlated? So yes, in fact, these are still very correlated. They're still very strongly correlated. It's just that the correlation, there's still a strong correlation. So every time one is changing, the other is changing. And the important part here is the fact that in the Pearson correlation, we were normalizing by each like variance of X and variance of Y. And for that reason, even though it looks like, I don't know, one is maybe more correlated than the other, but because you divide by variance of X and variance of Y, then they end up having almost or exactly like both correlation of 1. The only one is the middle one, which is undefined, because at that point, if you always get no variation in one of your x or y, then if you remember the equation, you divide by the variance of x and the variance of y. And if that variance is 0, that there's no change, then it becomes undefined, divided by 0. And then you have a bunch of other graphs here, and that will be part of your homework. And I'm just kidding, but yeah, these I will say are less correlated or very little correlated. Although it would maybe be tempting to call this correlated, but these are, I will say maybe not exactly 0, but they're very uncorrelated. Okay, so multivariate is an extension from that. So I talk about univariate. So in univariate, you have, let's say, age and the weight, and then you're looking at this. But in many cases, you have multivariate. So x and y may be like x may be language, and x1 may be looking at sentiment of in the language. X2 may be looking at I don't know, is it about the past or the present I'm talking about? So these could be all of these from lexicon, like LIWC, like description of the language. And maybe in the image, I could be looking at features like, is it about a person? Is the person smiling? Where are they looking? So these are a bunch of random variables. And so each of these, you could, a lot of time we call them features. In a non-statistical way, we'll just call them features. And so if for one view X and one view X and one view Y, or one modality X and one modality Y, and then everything we described earlier, it will still exist in the multivariate sense. So one thing is the covariance matrix, which is like within one modality, within modality X, how are these different random variable, how are these different features related to each other? So when I change, I don't know, the sentiment, does it change also the way, I don't know, how often I talk about the future, like, or how often I use, I don't know, first person pronouns. And so are they varying together or not? I mean, this matrix, the diagonal of this matrix will be how each of them are varying with each other. So it will be 1. And then if really none of them vary with each other, then all of the off diagonal would be 0. So that's what you get with a covariance matrix. The more interesting is the cross covariance matrix, because now it's not comparing X with itself, but it's looking at X and Y. And so for looking at how, like, if the language, if the sentiment is very positive, how does it change with me being a man or a woman, or me being smiling or not in the image, or me having a certain age, or me like, so how is all these features that I have, how do they vary to each other? How often do I get more of the positive? How does it change on having more smiles? And so that's what this matrix is going to be. And so this is going to be an interesting matrix. This matrix is and to show it visually, this matrix, the diagonal will be how X1 and Y1 vary to each other, X1 and Y2. The thing is, the ordering should not matter as much. So I should, like, if I can reshape re-swap the order of this. Although after I decided on order, then I should be consistent afterward. But here, like X1 versus X2 is just arbitrary. I pick X1 to be the positive words, and X2 may be negative words. But the more interesting is to look like inside this, how is these correlated with the other modality. So this is the covariance. And I'm just gonna, before I get into the CCA, which looks at correlation with this, as you remember, correlation, what was correlation? Correlation was covariance of X and Y divided by the variance of X times the variance of Y. So it's going to be a matrix like this divided by a matrix like this multiplied by the matrix of the Y. So you can already know how the correlation could be computed. Now I just want to define that the trace is defined as the sum of the element of the diagonal. I just want to define that. So by the way, the trace here, what will be the trace? Because here is the trace is 1, like the diagonal is always 1. And so the trace will just be the multiplication of these, which is, so that's the trace, just the diagonal of this. But so PCA is what you all know or have worked with in this kind of multivariate world. PCA is, the idea is that you have two set of points, point clouds or scatter plots. And so you have samples. And let's say for now, I have here, I have PCA. I will do it on 1 point cloud. So I have 1 point cloud, maybe all my language data. I have all my language data. And let's say I have only 2 variables, X and Y, okay? And X and Y. And so principal component analysis is this idea that although X and Y were looking at, I don't know, positivity, and I don't know what will be this one, like language, another language features. And then although I have defined these features and that's how I measured it, that's maybe not how the variance is happening. And so PCA is about looking where's the variance happening. What is that direction where most of the variance is happening? And clearly, most of the variance is around this axis. And so that will be called your first eigenvector. And then the second eigenvector will always be perpendicular to the first one. And that one will have less variance happening there. So this is a lot more interesting to study this. If I was to look at factor analysis, I would probably also study this kind of where the variance is happening. So officially PCA converts a set of observation of possibly correlated variable into a set of value which are linearly uncorrelated variables called principal components. And so I showed it for 2 different point clouds here. Eigenvectors are orthogonal, and the first couple of eigenvectors usually explain most of this. And the low eigenvalues mean less information. And so maybe it's just noise that is there. So maybe I could just remove the noise. Eigenvalue decomposition. I want to describe it because we will reuse it when we talk about CCA. So if you have a matrix A of n by n, as there exists a non-zero vector x in such a way that a times x is a scalar multiply of x. So this is another way to say it is that I have my matrix A that I'm trying to learn what is the eigenvector, and if I multiply by an eigenvector, then I should be able to be equal to multiplying the same eigenvector by the eigenvalues. That's the intuition mathematically. With one way of solving it is in such a way that if I have my original scattered data all around and I was to find this one eigenvector, then the multiplying by the eigenvalue would be equivalent to multiplying all of my data by that eigenvector. So that was another intuition. And that what's nice is to solve these, there has been a lot of interesting ways to solve this. One of it is single value decomposition, taking your matrix A and discomposing it in columns U. The columns of U are the eigenvectors of A times A transpose, and V are the eigenvector of A times A transpose A. And so this is, I'm going a little bit fast on this. This is probably for most of you just a quick reminder that of these. But the thing that you may or may not have worked on as much is canonical correlation analysis. And it is very interesting because in many problems where you have multi-view learning, you have some demographic and then some response to surveys. And so you're trying to match how the demographic align with different aspects of surveys. Or in our case is that you have audio and video and you want to see how these correlated to each other. And that's really, for us, when I think of multi-view, I think of multimodal, but in the more general sense, is multi-view could be for any type of data. So canonical is about reduce to the simplest or clearest schema of possible. And so correlation analysis goes in 3 steps. And so I have my text and I have my images. And then for now, I could call it unsupervised, but it is really paired data. So it has some kind of supervision. I have this paired data. And my goal is to learn an embedding where these are these embedding, these representation for image and text are going to be as correlated as possible. That's the first intuition, but it's not the exact one, and I'm going to clarify it. But at a high level, you could say, I want to have these embedding as correlated as possible. By correlated mean is there's increase in one, then it also increases in the other, or if it's positive correlated or negatively correlated. So if it was, the idea is to learn 2 linear projection. So I have my features for X, my feature for Y, so text and images, and I want to project them. And for now, I will just go with linear CCA, which says I have a linear projection. So I have already my embedding maybe of Word2Vec and CNN, and I just want to learn a linear projection of the 2. But I want to learn these projections so that these 2 projections, and by projection, I really mean representation or embeddings, these 2 projections are as correlated as possible. And that's the first way. And that's, if I was just to do this, it will not be called canonical correlation analysis, it would be called correlation analysis, because this is just how these 2 are as most correlated. But isn't there, and this is, I say here that it's the 2 embeddings that are correlated, but mathematically, it's also, you can imagine that it's the projection. So I have my X and I project it, and then I want these projections to be as correlated as possible. So this is the first step, and just the intuition there is I want these to be as correlated. So I have X and Y, and X and Y are, let's say for now, I have my, I have paired data, and for the X and the Y, and let's say for now, X and Y are in 2D. Y is in 2D and X is also in 2D. And the correlation is such a way that if there is an increase in X in some direction, that there will also be an increase similarly in Y. That's the main idea, is that you find it that every time that if there is a change in X, it also has a similar change in Y. That's the idea of correlation. So maybe if I have loud, very, like, let's say that X was about audio and V was here the audio and the visual. So it says stronger, very strong loudness and also maybe high pitch, very strong loudness and high pitch. And in visual, what you see is an increase in eyebrows, but a decrease in smile. There is a lot less smile, but there's an increase in eyebrows. So eyebrows goes up, but a reduction in smile every time that there is a very, very strong, and like I may say, maybe every time there's a reduction in my loudness, and my example here was pitch, although the example I was imagining was closer to being this way. So maybe the next time I present it, I will show it that way. So this is the correlation. This is just if it was correlation analysis. But in our case, and that's the beauty of canonical correlation analysis, is that I will not just learn it. And this is the same canonical correlation here. I'm just before I get into the second one, I just want to remind you correlation is covariance and variance of each of them. So how well do they vary to each other? They're just normalized by each of them. And if these are already normalized, then you can we can rewrite this because if the data has been already normalized, here what I did is just a rewriting. It's like there is this data, initial data that I have, and then I projected this y, and that gave me my hy. I took my x and I projected it and gave my hx. And then similarly for the variance on x, variance on y. So I'm doing this just because it's kind of everybody will often change the notation to something like this, which is like your covariance matrix and your variance cross covariance matrix and your covariance matrix. And so you often will see it this way, but these equations are exactly the same with just the normalized data. Now, the reason I go there is that I want to say that the second intuition is that I have hx and hy, and I could say, hey, I want them to be as correlated as possible. But there may be more than one way this data can be correlated. And it has the beauty of canonical correlation analysis is to say there's maybe more than one way that the data could be correlated. And so we want these multiple projection of the data. And so you have this data, and I will find multiple projection. Each of these projections will be orthogonal with each other. So I'm going to learn like these multiple projection, but I will learn them in such a way that my first one may be the most correlated, the second one is the second most correlated, and third one, third most correlated. And so the beauty of it is that there may be more than one way hx and hy will be correlated. And then I just need to find a way to enforce that these will be orthogonal or canonical. So by canonical is the simplest, and how to make it simple is to make it orthogonal. If you didn't make it canonical, then they could be like these could be like, but now if you make it canonical, then they're all. And that what it means canonical, it mostly means that hx, one, if I multiply one by the other, then it should be 0. That's the idea. And so another way to make it is to say that this whole thing, if everything, it takes a little while to realize it, but I want them to be canonical. What it means is that hx, if I take two of them, they should be 0 if they are two different ones, there should be 0. Otherwise, there should be non-zero. So this whole matrix, in fact, I'm going to force it to be 0, and I'm only going to focus on the center part of it, on the trace. And so because everything else, I want it to be 0. And so I want only focusing on the trace. And so I can rename, and I can rewrite it this way, saying I'm going to focus only on the trace, but I'm also, because if you don't add this other one, I'm also going to make it in such a way that since this subject is invariance and scale, I want to add this constraint that these should be equal to identity. I will make it as a constraint. And then when I do it and make it as they are equal to identity, I'm also enforcing that the off diagonal of this are 0. I'm forcing it by having this one there. And so the canonical correlation analysis can can be written as maximizing the trace. That's really what I'm maximizing, in such a way that the covariants are unit identity matrix, and also that the off diagonal are 0. So that's what I want to optimize. And so how do I see this visually? Specifically this part here, how do I can show it visually? I'm doing it in such a way that all of my I make it so that here, I make it so that these are identity, and I'm making it so that these are off diagonal are 0. And then I'm optimizing to maximize these. I want these as large as possible. So I want these as large as possible, while keeping all of this 0, and then an identity for the variance here. And so how do you solve this? And I don't know, you're probably a little while you look at these optimization problem, but when you see maximize and then subject to some constraints, you can probably know that one of the ways to optimize this is the Lagrange multiplier. Lagrange multiplier, which is translated as the barn, the multiplier of the barn, but no, Lagrange is probably the last name of the mathematician who did this. And there, what it is the idea of this is that Lagrange function that is defined as what you're trying to maximize, and then it has two parts of it. Each of them has these Lagrange multiplier, and these Lagrange multipliers will allow you to define those stationary points. And I'm not going in all of the detail, but once you get this into a function, which is, this is your loss function, then now I can start and optimizing like you do optimizing many of them by like looking at how they change, look at their gradient. And then when you do from that, when you force them to be as 0 as stationary point, then you can get this. This is just some simple, interesting mathematics that goes. But what's interesting in this is that it is in fact very related to SVD. To solve for this equation is in fact very related to SVD, because what you have is these eigenvectors and then these eigenvalues. So you can solve CCA with SVD decomposition, and so the SVD can nicely take on, and so you can take this part here, and that will gives you the decomposition. So so the canonical correlation analysis, the nice aspect of it is that it finds multiple ways that things are correlated. So in the spectrum of coordinated representation, I'm not forcing the representation to be equal to each other. I'm not forcing them to be completely correlated to each other, which will be kind of equivalent to just saying multiplying, so almost the same as the other. But here you're saying, hey, that there's more than one way that they can be correlated. It's still, in the big scheme of things, it's still relatively close to joint representation, but it allows a little bit more loose coordination to that. So these are the three main intuitions for canonical correlation analysis. So linear projection that maximize the correlation, but each of these projections are orthogonal, and you make it a unit variance of the projection vector. The unit variance was also something we would do, if you remember, for the word to vec when we were comparing the projection. So so now this is CCA. What's really nice is like, let's look at extensions that are non-linear version of this. So the paper in 2013 that got quite popular, it was an extension of CCA to make it a non-linear version. And in this case, it's not just the linear projection, but I will also have a nonlinear, and I'm only putting one nonlinearity, but there could be many more of them. And so the objective function is still to make my loss function, and because I have paired data, my loss function here is still going to be about the correlation of these two to be as correlated as possible, because if it's paired data, I know that this sample X is supposed to co-occur with Y, and so I will want there to be as correlated as possible. And for this, you need to compute the gradient of these between h of x and the u. And then you can, after that, once you've done that, as long as you get that gradient, which we talked about in the previous slide, that this is something that can be analytically computed, then it's a gradient-based approach, and deep neural representation are all about analytical gradient. So if I can get an analytical gradient, then I can propagate my gradient, and then everything goes well. What is the beauty of it is that you can learn and just pre-train, and that was more like specifically how they did it in that paper. That paper came not too long after the multimodal deep learning paper. So at that point, there was this idea which is still now very popular in language, which is the idea of pre-training, which is the idea of like, let's pre-train on maybe a larger amount of data. So maybe you can pre-train on a text base where I have multiple nonlinear representation, nonlinear projection, and maybe a linear projection. And then eventually I'm going to a middle representation in such a way that I can recreate my text. I can pre-train that way, and then that allows me after that to fine-tune it. So I can fine-tune maybe just the linear projection, or I can fine-tune all of them. Now CCA, one of the challenge of CCA is that it's correlation. And if I give you one sample, like an image and a text, I give you just two samples, one sample from each modality, and I say, what is the correlation? I don't know. You're looking at an image of LP, and I don't know, and I don't know, like brown eyes. Is there a correlation? Only two samples, you can't. The correlation is undefined. It's like so the correlation needs a lot of samples. So if you are to do a batch-based approach, it becomes very important to do large mini batches or full batches, and then you do something like the Newton that we talked about. What's really interesting of that paper, an extension of that paper, is to start and not only pre-train with an autoencoder and then do the CCA, but you can do it together. And that I think is really interesting. Here's what is the loss function here? Look at this model. What is the loss function? You have the autoencoder for text, autoencoder of images, and then you have some coordination between the two. So definitely h of x should be good in such a way that it creates images, can recreate the image, or at least the image features. And here you have your representation in such a way that it can recreate the text feature. And but then you also have the loss here. And so if you are to train it, if you had to start, which of these three loss, so the losses there, the loss will have three parts. How well I generate the text, how well I generate the image, and how always they correlated. Training it, you could start with all three losses equal. You could start maybe with these two stronger, and then eventually you want it to be as correlated. This is kind of a smooth version of the previous approach. The previous approach, you do autoencoding, and then you do the CCA. In this one, you're kind of doing all of them together. But even though you do it together, you may not want to weight all the losses the same at every iteration during your optimization. So that's another thing to think about. And so as a CCA, you can always learn the CCA in a stack manner that we discussed before. I'm not going in the details of LDA and some of these MANOVA, but I will say in our world where everybody is using the same approaches and we're all based on the same set of tools, I really invite you to start looking at others. Sometimes they look like old work, but this work is very strong in the sense that there's been a lot of proofs and there's a lot of interesting results. And if you look at interpretability as one of the things you want, these statistical approaches can give you a lot better, and often they will give you interpretability that also have bounds into it, and so that really useful information. So, like let's say, for example, confidence intervals on some parameters. So, so I invite you to study a little bit more on this topic. I want to look at a sister topic, which is called Multiview clustering, because we talk about if you have paired data, so we call it unsupervised data, you have paired data, and you want to learn a representation. But clustering, and just this one is not yet the multiview clustering, it's just the clustering is the partition, it's the idea of partition a set of data samples such that similar samples are grouped together and dissimilar samples are divided. So the nice thing here, and that's in the world of interpretable models, the idea of data clustering is to not only learn a representation, but within that representation, what are the clusters, what are the groups on this? And so the basic version of this is k-mean clustering. And this is a simple clustering based on competitive learning, where things can be part of only one of the K groups, and it's an iterative process. So it's assigning, the idea is you randomly, usually, or you can have a warm start, but you can randomly set the middle of each group. And then you, for all the sample, assign them into one of the group, the closest one, and then you recompute the center of the cluster and you do it until convergence. Winners takes all, that's why it's competitive. The subversion of that is a non-negative matrix factorization. So the idea here is you have a matrix X, and then you want to factorize this in such a way where what you want is a non-negative matrix F and matrix G. And so in this case, you could say you will have some kind of basis or factors, and then you will have some coefficient for these factors. So you could see it also maybe as G being those different centers of the clusters, and F being as how much each of these columns of X or each of these samples, how much is it part of each of this. So G will have, let's say 10 different center clusters, let's say 10 different center clusters, and let's say you have 100 samples in X, and so it will say for my first sample in X, how much is it part of the first cluster, how much is it part of the second cluster, how much is it part of the third cluster. That's the kind of nice soft clustering that I'm talking about. And this F, it makes sense the most when the F is in fact non-negative, because in that case, if it's non-negative, then it's really how much I'm part of that first cluster, how much I'm part of the second cluster. For these, whoops, sorry. So for this, there's been many nice interesting extension of that. SVD does decomposition, but this one is not necessarily non-negative. In the typical non-negative matrix factorization, both the G and the F are going to be positive. In the semi-non-negative, then maybe just one of them is, and the second one will be positive. If you go with the example I was saying, then the F, how much I part, how much is it part? I could be also negative kind of or positive, and then there's the convex version of that. Just to the semi non-negative is interesting because I like it because it also, you can go be both positive and negative in the way each of my cluster are defined. And so, and you can do it in a deep way. So there's a nice paper on a deep semi-negative matrix factorization. And it's deep. They call it deep, but it could be like multi-factors. It's like you kind of have NMF for one factor, NMF for another, and NMF for a third one, and that's deep in that sense. I will say one direction I like is the idea of learn the data partition from multiple view. So up to now, this is just about looking at this clustering. But what if I have multiple view? That's interesting. So it's not just I have all my language data and I want to cluster it, like the classic is topic modeling. I have a bunch of web pages and I want to know topics that are discussed. But here it's interesting is I have maybe the text of these and I may also have images in these web pages. I can also have maybe audio associated with it. And I want to do the clustering based on all those three modalities. That's the interesting part. And for now, let's say that I have paired data. So I know that an instance, I know that each instance, I come from the same audio, text, and images for now. And so the principle of multi-view clustering, two important principles, is the first one is consensus principle. You want to maximize what is consistent across multiple view. You want to group together information that is, so in each modality, I can have many dimensions, many features, but I'm gonna, let's say I have for view one, I have a lot of features, and for view two, I have a lot of features, but there's a subset of these features that have a consensus, and so that they're like similar. But also, multiple views need to get more comprehensive and accurate description. So there's also that there's complementarity in between the view. So there's consensus and there's complementarity. And so the multi-view subspace clustering, which is one way, one type, or one approach, learns a unified feature representation from all view subspace by assuming that all views share this one representation. So you have all of these views that have a subspace for it, so like kind of an embedding for each, and you're doing it in such a way you learn this subspace so that it learn to be able to predict that unified representation. And so how to enforce data clustering in our multimodal data, which is very interesting. So I have this multiple modalities and I want to make it in such a way that that data can be easily clustered. So I want to learn a representation of text and learn a representation of image in such a way that there will be a natural clustering in my data, and that cluster will be consistent across modality. And so one paper that you invited to look at, which was one of the early one in that direction, was the deep matrix factorization, which you have a visual, visual features. You have, in this case, the language was represented in a discrete way, and these two will be taken together. Here, the one will be embedded, but then finally you will find this way in such a way that there is a nice factorization of your data, and then if you do that at test time, it also helps you at test time for the image tagging in this case. I invite you to look at these other approaches, because I don't have time to discuss all the different ways, because one way that we look at it is as a subspace, and then the subspace in such a way that there is a nice grouping, but you could also have in it a graph. And so the sub-embeddings of each view is in fact a graph, and you want to do it such that the graph has a nice way of being clustered. And that's a little bit closer to what we discussed also last Tuesday. And so I invite you to look at these approaches. And it's really nice because you can do that in such a way that you can also bootstrap between this. So this is just the idea that you will do let's say the clustering, you get some knowledge of it, and then you use that knowledge for another modality, get the clustering, and then do the knowledge and do this. This is a kind of a co-training way to do that. Okay, the last part of the lecture that I want to discuss today, this is about the autoencoder of autoencoder. And this is an extension, and in the spectrum of coordinated. So we talk about having very strong coordination, like cosine similarity. We talk about correlation. We talk about canonical correlation. We thought about clustering, which I would say is like a little bit loosely, so, or even graph-based. And here we'll talk about having it it has a little bit of that same intuition of latent space, but it's a nice extension of that. So just the quick reminder of the deep CCA. The deep CCA is the idea that you learn, you have an autoencoder, and you have the autoencoder, and then you force it to be, at the same time, you have a third loss that also makes it that it's correlated with orthogonal projections. But multi-view latent intact space is, the intuition there is that, for good or for bad, it's the intuition that there is this non-noisy, like this real intact representation space that exists, and then each modality or each view is kind of a slice of that plus some noise, like that makes it so. And one view of that is like, I have an intent. I really want you guys to love multimodal machine learning and understand coordinated representation. So that's my intent. That's in my brain. You don't observe that. But there is this intact, I don't know how, hopefully intact space that I have of representation that I have. But when I talk, I'm trying. This is me sharing. This is a view of what's not visible, but this is a small view of what's not visible. And you see my expression, and you hear my voice, and all of these are all different view of that same intact space. So I have this intact space, and I said something. You see my nonverbal, my acoustic, and that gives you a noisy version of what I want to say. That's the first intuition I want to share, which is the intuition of intact space. The other one, which is even cooler for this model, is that that intact space is different for every instance. So if you look at the first 5 minutes of this lecture, I had one message I wanted to share. That was my intact space for that first 5 minutes. But the next 5 minutes, and now this current 5 minutes, I have another intact space. And so at every time I have this new intact space, and that's it's a different. I had a different intent at each of these 5. At each of these 5 minutes, I have a different intent, and you do a different view of that. So if I was to call it like H, my intent, my hidden intent, and it's intact, it's clear, it's in my brain, it's clear what I want to share with you. But HI is different for, not I here is the different views, but that H is going to change at each instance. So there's an intact representation, which is complete, not damaged, but the views are only partial representation of that. That's the first intuition. So the autoencoder of autoencoder, or autoencoder in autoencoder, is you have an autoencoder. That's the typical autoencoder. So it goes ahead and it encodes your data and decode it. And then I have this intact, like this intent, and I have it intent, and for each instance in my training, it may be different. That's another part of the intuition. And so the idea is for each instance, I will take this intact thing that is joined for both of them, and I will degrade it to degrade it for the text and degrade it for the image in such a way that the degraded representation of what I really wanted to say to you, that degraded representation has a nice, it should be as close as possible to that representation here. And then I also at the same time want my loss. So I have 4 losses. I have my 2 autoencoder losses. But the beauty of here is that the way I'm coordinating it is that I will force it to be always have something in common that I can degrade and be close to each other. And the total loss has both of them. And the latent, there's also this latent variable age. And the minimization here is going to be challenging because age will also at test time, that would take a little bit, but at test time, age will also need to be inferred because it is not observed. Age is not observed. And so at test time and at training time, but at test time, usually age, you would like it to be a parameter. But in practice, age can be at test time also inferred from that. And you may need some interactive way to do that. So that's the autoencoder. And so in the scheme of things, you can see how this one has less of a clear match. I mean, these don't need to be matching exactly. It's just that there's a degraded, maybe sometimes it's more degraded than others that goes with it. So thank you very much for your attention.